What is the proof of work system? The proof of work system is one that requires miners to spend some time doing computational work to add blocks to the chain. This has the benefit of deterring dishonest peers from replacing the blockchain with corrupt and invalid data. To explain how dishonest nodes are dissuaded, consider that in our decentralized blockchain, any peer has a capability of submitting a new chain to the system. As long as that chain is long enough and contains valid hash data, starting from the Genesis block, that chain will be accepted by all the peers in the blockchain network. Yet, to discourage dishonest individuals in the network from taking over the entire blockchain with a corrupt chain in their favor that actually has valid hashes, the proof of work system makes it computationally expensive and almost ridiculous to do so. The proof of work system makes it so that individual nodes in the blockchain can put in a manageable amount of computational work in order to add a block. However, for a dishonest node, the proof of work system makes it vastly unproductive to try and take over with an entirely freshly generated chain. Many cryptocurrency blockchains, such as Bitcoin, use a proof of work system inspired by a system called Hashcash, created in 1997, that was used in order to prevent email spamming, as well as denial of service attacks that would overload web servers. A proof of work system inspired by Hashcash works like this. At any given point, there is a level of difficulty in the blockchain system. Depending on this difficulty, when miners try to add a new block, they will have to find a hash value for this block that matches this difficulty. For this matching, miners have to find the same number of leading zeros as the current difficulty for the generated hash of the new block to add to the chain. Finding this certain number of leading zeros randomly becomes exponentially harder as the difficulty itself rises. So in order to solve the proof of work, a miner will have to generate a ton of hashes in order to eventually find one that satisfies the difficulty. They will generate new hashes for the same block based on the block data, as well as an adjusting value called the nonce. By changing the nonce value, the miner generates new valid hashes for the current block and its data. A nonce is a term in cryptography to refer to a value that can only be used once. Since every unique nonce value will generate a unique hash, the nonce can indeed only be used once to generate that new hash for the block. The nonce value starts at 0 and increments upward until a nonce is used that has a matching number of leading zeros according to the set difficulty when it generates the hash. This nonce value is then stored as part of the block, and this act of generating new hashes with changing nonce values takes quite a bit of computational work. So the act of spending this computational work is part of the reason why adding a block to the blockchain is called mining. And once a miner has successfully mined a block, they will submit their block with the found nonce value to other miners. Once the other miners know this nonce value, they can quickly verify the validity of that solution and add the new block to their chain. That way, they don't have to redo the same computational work once they receive a new block to add to their own blockchain and stay up to date. Because of this difficulty setting, blockchains also have the ability to control the rate at which new blocks are added to the system. The higher the difficulty, the longer it will take for miners to add a new block. Likewise, the lower the difficulty, the less time it will take for miners to add a new block. Bitcoin, for example, has a goal of adding a new block to its blockchain at around every 10 minutes. So as more miners are added to the network and more computational power is devoted to the system, the higher the difficulty of solving this proof of work algorithm becomes. The constant adjustment of this difficulty setting keeps the rate of blocks being added to Bitcoin at a steady rate of every 10 minutes. This leads us to the interesting scenario of what is called the 51% attack on a blockchain with a proof of work system. The 51% attack is a scenario where a dishonest miner has more than at least 51% of the computing power of the entire blockchain network. Thus, they would have the power to replace the current blockchain with one in their favor. With this computing power, they could generate a long enough blockchain that has solved enough proof of work puzzles in order to generate a valid blockchain that everyone will have to accept. However, the proof of work system makes such a situation so computationally expensive that it's absolutely ridiculous to spend that cost in order to try and benefit from manipulating the blockchain. For example, to take over the Bitcoin network at this point, in all of its collective computing power, current estimates from GoBitcoin.io are more than $6 billion as of the beginning of 2018. Plus, the attacker would undermine the very system they were trying to benefit from. So at that point, how do they even benefit from the system that they gained control over? Overall, the proof of work system deters dishonest miners in the blockchain network, and it also helps us control the rate at which new blocks are added to the chain. So let's get to implementing the proof of work algorithm as well as nonce values next.